you get these lines for the different.
It's a rather spectacular proposal, which is to explain dark matter without new physics. So Glennys, are you ready?
Yes. I really appreciate the enthusiasts who are still here, because I'm really, at this point, very much need input from experimentalists. For quite some time, I've been thinking about this possibility that dark matter is actually a very special bound state of 6 quarks. And as time has gone on, I've worked harder and harder to see if there's any showstoppers or no-goes or anything, and tried to find experiments that you could use to detect it. It turns out, strangely enough, it's very, very hard to find it and know you found it, basically because it's too much like neutrons and there are too many neutrons. In any event, so at this point, I feel like the cases where you could make a reliable prediction for the production rate and find it, you just cannot do that technically with a non-dedicated effort. And so I think it's come to the point we need to add a little gadget to one or more of the LHC heavy ion detection experiments. Also, I'll now try to justify that to you. Well, I'm not going to spend, because I really want to focus on the feasibility of this particular experiment. I'll go very quickly through lots of otherwise interesting topics. I'll show you a few new things. One is now there's a more reliable calculation of the mass, which lands it right in the right range. That's super nice. I'll talk a little bit about why it's possible, but very, very briefly, why we would have not seen it. One of the strong motivations is that the calculation of the ordinary matter to dark matter ratio is a first principles calculation with sort of order 1 uncertainty. And when you do it, you get an answer that's basically agrees. So I'll show you that because that's a strong motivation. A couple of things I won't do is show you that dark matter, Big Bang nucleosynthesis works the same way. So the usual idea that nucleosynthesis rules out dark matter made of baryons is just not applicable, essentially because it's sequestered in this very special non-baryonic-like form. So it doesn't bind to nuclei and stuff. And then another important possible no-go that turns out not to be a no-go is the neutron-star mass-radius relation. Mabude Sharbat and David Lashmi have done lovely work on that with a few hangers on, which should be coming out soon. And fascinatingly, it might even improve the fits. It very naturally gives the observations that binary neutron stars are sensitive to of how flexible the material is. I'll briefly mention the constraints on dark matter just to show you what's the interesting parameter range. And then this is going to be the thing I'm really trying to lead up to. So that's my way of apologizing for not being complete on the other things. The gist of the idea is that in this very special state, in order to have the state be in a fully antisymmetric state under color, flavor, and spin, it's a unique state. And by Fermi statistics, this is essentially the only state that only choice of flavors and numbers of quarks that can be in this state. And then there's a whole class of arguments under the framework of Mosapac channel that when you're in that state, you get extra strong binding. And so that motivates the idea that it might be tightly bound. The problem has been that it's very hard to calculate the mass. Lattice gauge theory is only able to do it in the quark mass of 850 MeV limit because it's just so difficult. And if there's a dilambda loosely bound state, a molecule like deuterium, which one would assume there is, then that makes finding the actual lowest line state very, very hard. Anyway, so, and there have been a few different very perplexingly, very, very different from each other efforts to use QCD sum rules. My student Ziwei Wang has really dug into this, and we've discovered that they both made sort of a blunder effectively. And Ziwei has redone the calculation now, and interestingly gets it, it turns out to be just in the range which would be most interesting, about 1.8 to 2 GeV. This is showing the sensitivity of the result. It's sort of, I won't go into it, but in any event, this can be improved by doing a next to leading order calculation, so you get predictions that aren't so sensitive to these sum rule model parameters. But the picture to keep in your mind is that if there is a Sexaquark and it won't couple to pions because the pions are isotriplets and it's an isosinglet. And so potentially it's considerably smaller. And in any case, it's the best way to think of it is a triple diquark. And it's such a different configuration from ordinary hadrons that the amplitude to convert between or coupled between sexaquarks and nucleons would be expected to be small. Let's see, move to my next. Well, I'll just say the basic point is that it's tricky to my monitor just did something weird, but I assume it didn't do it to you, just to me. So the big thing is that it's similar in mass. It's around twice the proton mass. This would be the number to keep in mind. It's very similar to the neutron, but it just scatters less strongly. I won't go more into this right now. If you look at the limits that you can place, so there's two different ways you can imagine having access to this state. One is if nature provides it to you through dark matter hitting us. Another one is if you want to make it in an accelerator. When you make it in an accelerator, since you start with ordinary baryons, in most instances, you're very strongly suppressed because the breakup amplitude of an S into virtual lambdas is very, very small because the wave functions are so different. And there have been estimations over time, but the effective vertex for this would be expected to be of order 10 to the -6 or smaller. Ziwei and I looked at limits from deuteron stability, and there's, and all of that's fine, and most of the mass range. So I'm not going to go into that, but just so you understand that that has been studied. You can go through there's a huge literature on people having done searches for the H-dye baryons, so you can go through them, and interestingly, not a single experiment would have been sensitive. Well, there's one experiment that would have been sensitive, but it was nowhere near sensitive enough. I mean, had it probed to a much deeper level, it potentially could have. I won't go through that again for the same reason. So here is 2 minutes on the this dark matter to baryon ratio. In this picture, to 0th approximation, the picture is that all of the strange quarks in the early universe and the quark-gluon plasma wind up inside the dark matter. So this would be a dark matter particle. But since the strange quarks are heavier, their abundance, they constitute about 30% of the quarks, and 70% is up and down quarks. And so there's a little left over up and down quarks, and that makes the ordinary matter. So you can see it's a super simple idea. You have to improve the calculation a little bit by taking into account the fact that even in thermal equilibrium, there's a competition between the strange quarks being in the dibaryon, in the Sexaquark, versus being in 2 separate hyperons. So that's a totally calculable correction, because again, it's just stat mech, and that leads to this formula. And then when you plug in the numbers, this is the important picture. This is showing the temperature. Oh, and of course, this presumably evolves as the temperature goes from being in the quark-gluon plasma above around 170 MeV to finally being totally in the hadronic stage at around 140 MeV. And so it's you might think it could be sensitive to where to how that transition happens, but doing this kind of just calculating it as a function of temperature, this is the temperature here, it turns out to be quite insensitive. And just because probably the color code isn't very visible, it's most sensitive to the mass of the Sexaquark. And I think there would be order of 2 uncertainty anyway, because at high temperatures, as the vacuum condensate of QQ bar condensate is turning on, the Sexaquark mass and the lambda mass, the hyperon masses won't necessarily respond the same way. But so in this simple approximation that they respond the same way, this is the prediction. And the black line is the right answer. And so with no free parameters, you simply find yourself in the right ballpark, which certainly motivates taking it seriously. Standard dark matter detection doesn't apply because it's so much more strongly interacting that it gets absorbed before it gets down, let's say, to the very deep underground detectors and so on. So you have to reanalyze it. This is the latest analysis. Another complication is that the interactions are non-perturbative. We assume they interact through the exchange of a omega-phi resonance that, the vector meson that we all know. This mass is around a GeV, so one could say that generates some effective interaction with nucleons. Now, this parameter alpha would be then a product of the vertex for the Sexaquark decoupled to a phi and the phi nucleon coupling. So you have an idea of what range that might be in. And so the most natural range, it seems to me, is for alpha to be somewhere between 0.01 and 0.1, or it'd be a little hard for it to be as big as 1, but one can sort of think about it. The CMB, actually, this is now plotting this value of alpha versus the Sexaquark mass and showing you what the limits are. This crosshatched region is not yet excluded because the analysis is quite detailed. But basically, when we complete it, it will be relying on the fact that cryogens don't heat up due to Sexaquarks just penetrating the dewar and then scattering off the cryogen. I think we'll be able to exclude this whole range. So I'm going to talk as though the interesting range is really below about 0.03. This green is only excluded under, if it's a repulsive interaction, you have some additional models. But anyway, it gives you the idea that the interesting range is available. And so then we can try to ask, how could we possibly try to find it? So roughly speaking, the discovery strategies, this is kind of summarizes them, the various ones that I've spent time thinking about. Well, the most striking thing is if you produce one of these things and it escapes your detector because it's this neutron-like thing and you don't notice it, then it's carrying baryon number and strangeness. And it's got a specific connection. If it's baryon number +2, then its strangeness is -2 and so on. So the first thing one might think about is various strategies along that line, looking for correlated imbalances and so on. Well, the bottom line is that conceivably this could be a strategy, but it looks to me like it's inherently not sensitive enough, just because the mis-ID has to be so low for this to work. One thing that seems potentially very promising is in upsilon decay to produce 2 lambdas and then for example, an anti-Sexaquark or the opposite, 2 anti-lambdas and a Sexaquark, which then escape, and then with pions, and then if you can reconstruct the invariant mass, you could even hope to find some sort of peak or a shape that's shows that it's sensitive to the mass of the Sexaquark. if you wanted to do this as an exclusive reaction, and this was actually looked at from Farrar with no pions, it turned out that Farrar couldn't do it as an inclusive reaction because they didn't have enough, essentially they couldn't measure the momenta well enough. Then there's but if you do it as an exclusive reaction, there's something like a factor of 10 to the 5th penalty in the statistics. It's still a small, even if it's inclusive, the branching fraction would be estimated to be around 10 to the -7. I really hope that Bell too will look for this. I believe they are. But one of the things that's not good about this reaction is that you can't reliably predict the rate because it depends too much on how this hadron forms. One can make an estimate that's in one of my papers, but anyway, so it's something I don't like about it. There were various other schemes that I looked at with other people and so on. So the thing I want to emphasize today, which I think is really the right thing to do, is to take advantage of the fact that its production in heavy ion collision, where really the system is a thermal system, has to be pretty predictable. Let's say it's roughly like the prediction of a deuteron within the uncertainties of the various production models. Then we know there's actually quite abundant. The number of deuterons per unit rapidity is about 0.1, and so you'd expect the same number of those. So right away, we have a goal for what the rate is. And so here's the trouble is you can't do things like try to look at all of the strangeness in the whole event or look at missing energy. That's just way too much other sources of missing that. But what you could conceivably do is the following. Imagine here's your colliding beams, and that's schematically showing particles that, you know, all the different secondaries. And amongst them, let's say there's a Sexaquark or a neutron that I showed in red. And it's got interactions with the material of the detector. And so it will sometimes scatter. Now, let me call lambda the scattering length such that it makes the detectable scattering. One has to work harder to decide what that should be. Anyway, if it makes a detectable scattering and actually effectively gets removed from the flux that you would have predicted based on the production. In that case, the number of neutron interactions will decay with distance like that because it's getting removed from the neutrons, where this is some sort of effective inelastic scattering length. And the Sexaquarks, which are scattering so much less and also are produced less, so there's some factor here of order 30 in the heavy ion, but up to a factor of 10 to the 6th if you're not in this quark-gluon plasma regime. Anyway, so this one is got a much lower interaction length, and therefore it will be flatter. So just to give you an orientation, the distance here at which these two curves cross so that it's no longer dropping just like it was only neutrons and it shows this residual leftover piece, that, and if I put in the pessimistic numbers, pessimistic means it's weakly interacting, that makes it harder to detect. But in the pessimistic numbers that Yukawa was 10 to the -2, then I can estimate this crossover distance, and it's about 2 meters. So the general idea would be to make a detector with essentially 2 meters of iron or steel, whatever seems best to the experimentalists, where it should be put. You know, I put an actual picture because there's not a heck of a lot of room left in these chambers. You have to figure out geometrically what's possible. Maybe it could be a little more forward, but that may be not good because then you wouldn't they wouldn't get out of the beam enough out of their normal trajectory. So some work has to be done to work on that. And I would be so thrilled if people here would discuss this and sort of work on it. The requirements of this detector is that you don't want to be confused by seeing like a K0 decay. so that's what I meant here. You have to have enough material that you actually get this far out. The nice thing, by the way, I guess to repeat it, the thing that's really great about the heavy ion experiment is that you know that this is just a factor of 30, whereas if it was like a PP collision, this could be a factor of 10 to the 5th, and then it's very much harder. So, and then you have to go out here far enough that you can still see the low level of interactions that will be left. Anyway, that's I'll just make my summary list in the hopes that I've left enough time that we can talk. So the message to take away is that there may be this slightly bound triple diquark state. There are good theoretical reasons to think it might be there. Some rule calculation gives it in this range of where it would be effectively stable or stable. And then I showed you that if that state exists, it would be an excellent dark matter candidate. A paper that got a lot of sort of profile from two eminent people who made a blunder on this. They forgot that it's so hard to break it up. And so there was a paper saying that it couldn't be the dark matter, but that's just wrong. And so then there's a strong motivation. One could hopefully also in parallel, people at Bell will look for it, where it's more of a fishing expedition because you can't predict the production rate. But in the heavy ion environment where it's quark gluon plasma freezing out, that's just what happens in the early universe. And so it should be possible, there we can predict its rate. And so therefore, showing that it doesn't exist would exclude the model, or if you have the sensitivity to show it exists, you would demonstrate that this particle exists. So as I say, I left this note. You can see for the experimentalists, there's a lot to work out in these calculations back here to do a better job of modeling what the collisions would look like and what would be your cut to decide it was inelastic enough and so on. That part has to be figured out, and that's real work. If an experimentalist were to come along and say to me, oh, this will never work because no one will spend the money for this, or it's too big and it won't fit, or whatever, then I won't work on this, but otherwise I will. I'll be happy to. So thank you very much.
Okay, thanks a lot, Glennys, for for your update on the Sexaquark, which is certainly still one of the most fascinating dark matter candidates because it could work in the standard model if it works. So the floor is open for questions, and in particular, as far as I understand, from experimentalists, of course. So questions and comments, please go ahead. So let me start. So the reason why you think that heavy ion collisions are better than proton collisions is because of the thermal environment. Is that right? Because
it's because you start with, it would have to be central heavy ion collisions where you know you're starting with essentially a quark gluon plasma, because then it's calculable. Otherwise, it depends on this effective vertex for coupling it between baryons and the Sexaquark, which could be very highly suppressed.
So you're going through like an ensemble average production, sort of, if the early universe made, so one could take the viewpoint, okay, of course, chemical potential is very different in the early universe, but you could take the viewpoint, if the early universe made this, then our collision has to make it too.
Well, you know, that was my first way of thinking about it, but actually I discovered that thanks to the really beautiful data, I'm aware of it from, in my mind, is a plot from Alice, where it's so beautifully fit, just the observations from heavy ion collisions at CERN, central heavy ion collisions, the regularities of the number dense production with respect to the mass of the particle, for example, are so beautifully described. And so the same, if that's to the extent that that's coming just because quarks are there and then they make themselves into hadrons in a thermal way, then we can just use that directly, those observations, and just say, well, its mass is near a deuterons, so it'll be roughly produced at that level.
Okay, I see 2 hands up now, so let me start with the Debasish.
Yeah, can you hear me? Hello, can you hear me?
I can.
Yeah, okay. Just I want to know that you have made, the speaker has made a comment that we can have dark matter in this LHC detectors. I'm curious to know that if you are talking of this heavy ion experiments like ALICE and others, are you, is it more feasible to look into the forward region or in the central rapidity? This is just a curiosity because, yeah.
No, it's a reasonable question because LHCb, for example. So I spent quite a bit of time talking to colleagues in LHCb, and Stephen Lewet and CMS tried to look at it. The fundamental problem is not producing them. They're copiously produced effectively compared to most, most new particle things, because it is part of QCD. But knowing that that's what you've got and demonstrating that it's not just a neutron. I mean, right, if you try to, well, that's all I really need to say. So neutrons in the forward direction, to discriminate that from something that looked the same but was twice the mass, no way you can do that.
Mm-hmm. So what would be the decay products? I mean, what particles should one look? Muons
it doesn't decay.
Or high?
No, sorry. Okay. It doesn't decay. It's because it's stable. Otherwise, it couldn't be the dark matter.
Yeah, but then something has to be detected in the detector, right? How would I?
Precisely. So in the proposal that I'm making here, let me see if I can find my picture. Over here, the idea is that it comes along. If you imagine you had a neutron, occasionally, after on average 10 centimeters in iron, it will recoil against the nucleus that's there, and it will be deflected. You still won't see it. Also for neutrons, you don't see the neutral particle, but you could see that there's a small shower from the interaction.
Okay.
And so the Sexaquark would do the same thing, only with probably very similar kinematically, because again, just for the reason that they're similar in mass, but with a smaller interaction rate.
Okay, so you want to detect neutrons. Okay, I understand. Okay, thank you.
A way to think of it is look to see if neutron scattering decays exponentially forever, or whether there's a plateau that it hits. And I'm estimating that this distance is a distance less than 2 meters in iron. It could be as small as 1.4 meters, but it's not 100 meters, which would be impossible, but it's also not a little thing that you can just tack on.
Yeah, because for the experimentalists, they need some observables to look into. So ultimately something has to be detected. So here you are proposing the neutrons as the observable, right?
This neutron scattering, or the existence of scattering of neutral particles. Right.
Okay, thank you.
Yeah, I see several hands more up. Before there was also Ralf. Ralf, I don't see you anymore. Is your question already answered?
No, but yeah, partly, but I think maybe it's still worth just as a comment. Partly it has been answered, because I think if you look at LHC, the obvious place to do something like this is LHCb. You already mentioned that, because in LHCb, the interaction point is outside of the main experiment. So it's in front of the experiment, and there would be in principle space. I mean, in none of the other experiments, there is space.
I see, yes. A standard LHCb without, okay, I want to ask you a little more about that. Standard if you just use LHCb in a PP mode, then LHCb tells me they need so the regular use of LHCb turned out not to be helpful because they really need something like a muon trigger. But you're saying that geometrically there might be place for it. Okay, that's good to know. But
Yeah,
what about?
I agree. So I was thinking to add some simple detector on top of LHCb, because there would be space for this, and this could be something movable, so something very simple. And I think that would be maybe something that some people might actually consider to do.
Okay, yeah, well, let's talk about it when I'm sure that Marco is eager to get to the discussion of snowmass, but could we talk, Ralph, after, or we'll make a date to talk some more? I'd love to follow up on that.
Yes, we can, yeah, but I'm not an LHCb.
Maybe you know somebody.
I think that there are some LHCb people around here, I believe.
I was especially interested in ALICE just because they have such great control over the heavy ion collision part, right? What you want to do is essentially trigger on having had a central collision. And then
yeah, but LHCb is really unsensitive to neutrons, so I don't think this is really a good place to go.
Okay, okay.
I meant Alice.
Right.
Maybe I
said you would need this other, right. I don't think there's enough, I shouldn't say I don't think, there's not enough material in the detectors themselves, of course, on purpose, in order to have a big enough interaction length for the neutrons to be decayed in order to, right, you have to have something like 1.5 or 2 meters of lead or iron. And there's not that mass equivalent in any of the detectors. So it has to be an add-on outside. I was hoping maybe up above ALICE or in somebody's office, tear off. Looking at that picture, I mean.
So there are some more questions. There was one by Ian Deere.
Hi, I'm just curious, a naive question. So what's the fraction of energy will be carried by this particle in heavy ion collision? And also, does it matter if the speed of S particle does not matter? Because in mid rapidity and forward, the momentum distribution will be different, right?
Basically, the energetics are like for neutrons. And so in the central region, there'll be a few GeV or something like that. And it's very much not the regime that people who think about new physics usually think about. What was your other question? Sorry.
The momentum and the detection.
Oh, right, and what's the better, whether it's better to be forward or central? I don't know the answer to that. One would have to, I think the answer to that revolves around when there is a scattering, either of a neutron or an S, it gets deflected. If it doesn't get deflected enough, then this exponential decay doesn't help you. You need to be having a reduction in the number of the neutrons. And so you're looking for interactions where the neutrons will lose a good deal of their energy or scatter to a large angle. And so for that reason, I'm thinking maybe a lower energy, the central region would be better. But that's a calculation that, but you could maybe argue that a more forward, higher energy neutron will deposit more energy when it scatters, and that'll be easier. You won't have to worry about so much background. So for me, that's a still to be figured out question.
Okay, thanks.
And there's another question from, and I hope I get the name right this time, Tong Yi.
Yes, Tanguy.
Tanguy, sorry.
Yes, exactly. Glennys, it's something I don't understand. A neutron which has few GeVs, it will not just scatter, it will interact, it will produce new particles. What happened to the S? Will it do any hadronic interaction, or the cross-section is so small that it won't do anything, but if then it doesn't scatter neither? So what type of interaction and energy are you talking about in this plot?
It could, the way it would be different is that in the neutron, you can have, for example, they can make protons. So the baryon that leaves in a neutron scattering doesn't have to be the neutron. But otherwise, I would think the final state is sort of similar. The baryon that leaves has to be the Sexaquark in the S scattering, but just because it's scattering off of a neutron, there's stuff there that will enable the creation of final states. So I think that it ought to be modeled, but I was thinking that at fairly low energies, maybe you don't have to model it very carefully. But you're right, it's something that should be thought through. But to make a long story short, if it were high energies, I think it would be a little bit like scattering where on one side it's diffractive, that's on the Sexaquark direction, and it's just regular hadronic on the other side, on the neutron's direction. But at like 10 GeV of energy, I guess that would be sort of like elastic neutron scattering, or not so much elastic neutron scattering, but not highly inelastic neutron scattering.
Yeah, so maybe if you are really at mid rapidity, if the energy is not too high, then you don't get too much inelastic. But if you go a bit forward, then you get, you can easily get 100 GeV, and then you get standard QCD interaction producing new pions and so on, which might actually, if the Sexaquark do that, then it's easy to detect. You just have to,
totally. But so I guess, yeah, that's a nice idea. It would mean, maybe that's a really nice idea, a different idea than I'd had. I was thinking more of the scattering enabling you to tag that there had been an interaction. You want that, and so then you don't care much about how it scatters, and you want to somehow remove that from the beam, so to speak. By beam now I mean the flux of particles going in whatever direction your detector is, because if it keeps re-interacting, you're not going to get this suppression of the number of interactions. But I think you've got a really interesting point. Maybe the collisions themselves have a distinctive character. I mean, they would at higher energies, especially because you would not get so much forward production, I guess. Well, it would be fun to talk about. I think that's a really good idea, Tanguy. It might be a much better thing.
I don't know, if it's really a hadron, then it would just interact like any other hadron. But the cross-section, if you say it's small, for instance, can be different. And then if you have a detector which have enough material before or something, you can, I mean, that was the idea of Castor on Centauro, that you want to see a particle which has a different in the cross-section than what you expect from a standard hadron. And then if you see a tail of long, long interaction length, then you can see something like that. That's basically it's your plot.
That's exactly right. It's the totally. That's exactly right. Yeah. It's the difference is that the fundamental interaction isn't like of a very heavy particle, and you're not releasing a lot of energy from
this side, yeah, I don't know. I mean, if it's quarks inside, I don't really see why, at above some energy, why it will not behave like any other hadron. Or maybe you have good reason for that.
Well,
but,
if it's because this vertex for, if you think of the Yukawa vertex for dissociating it into two nucleons, that's super small. And so, I mean, into two baryons, that's very small. It's like 10 to the minus 6. So the way it interacts is through the exchange at zeroth approximation of a phi meson. And so if you could model the scattering of ordinary baryons where you somehow restricted the coupling to be the primary interaction to be the exchange of phi mesons, that would be a good model without the disruption of the S. So you're absolutely right. They'll be somewhat different, but that's why if you think of it as a central collision and in the rapidity plateau and the S is coming this way, then there won't be much in the forward direction because it won't tend to break up, but the exchange of that phi will break up the its partner nucleon, which will, the material the nucleus and the material, so then you'll have a lot of particles, final particles in that direction. That was the idea. Obviously, you'd want to really try to have the whole thing be insensitive to the details of getting that modeling right. And I was trying to do it more in terms of the counts of events, but it's certainly fair to say that maybe well, it'd be interesting to know how different the events should look, whether that would be an additional signature.
Yeah, okay, we'll discuss offline, but yeah, what would be of such an object? Yeah, if it has any, or if you say it, yeah, it has to have something. So yeah, what type of interaction? Yeah, okay, yeah, we can talk later, I guess.
I see, Devasish, you still have your hands up. Did you want to say more?
No, I'm done. I think that's the old one. Okay.
Yeah, no worries. All right, then, well, I guess then thanks again, Glennys, for giving us an update on this interesting option. And then I'd like to hand over to David, who has kindly volunteered to chair this little snowmass discussion that we're going to have now.